Hi, in today's video we are going to check my 3 years old lithium polymer pack. We are now floating full, and because this pack does not have any way to look inside, and I did it the last time about 2 years ago, actually more than 2 years ago, I want to take the chance and see how the cells are balanced, and then I want to try to find out how much capacity this pack still have after so many time has passed. But let us talk a little bit about this chemistry first. So lithium polymer, or people know them better as a cell phone or tablet batteries, was there for all the small devices we are carrying with us, and sometimes they have been used at the beginning to also give people a chance to store or to use lithium ion chemistries for other projects than just the small ones. 3.5 years ago I have ordered that pack directly from a Chinese manufacturer, and it was actually customs built. The pack, how it looks like, the box was at that time specified by my needs. So the only thing they sold me was a 48 volt 200 amp hour battery pack, and I could tell them exactly in what shape that pack should be assembled, right? Now we will actually look inside that box, and what do we expect to see there, and you will see there's nothing else than compartments filled with these tiny pouch cells, same you would find them in probably a tablet PC. There's a simple normal BMS built in there, and there is no communication or whatsoever. It is just a dumb battery, that's all. But it's already standing there since more than 3 years. I will show you then the date when it was powered up the first time, and can then calculate how many cycles have been done on that battery, and we will then also try to find out the remaining capacity after all those cycles. That time when I bought the battery, they advertised it so that the battery capacity will be 80%, at least 80% after 500 cycles. So 500 cycles in a solar application like I have it here is not much, but we will see and calculate how many real cycles we have on the battery pack. So we have actually now a total voltage of 58.1 volts here. That is more than 95% state of charge, and the controller is only floating the pack at the moment. And here I wrote it. The battery was produced in October 2017, and the first cycle was put on this battery on 27th February 2018. It's now a little bit more than 3 years, but a little bit more than 1,100 days. And how many cycles that 1,100 days are, we will then calculate together. But let's first take off the cables from the main breaker. Then we will secure the pack and bring it out to open it up. This is the pack. I have protected the terminals with the plastic covers so that we don't shorten them. And yeah, this is how it is built. Very nicely built in this steel box, and handles to carry it. It only has a very simple meter here, which shows the state of charge and battery voltage, but this is only very simple, so only voltage based and linear probably, so you cannot, the voltage is okay, but of course the state of charge doesn't say much about this real state of charge. So we have to open up some screws. Maybe I have to lay down on the side and Then let's see how this looks from inside. I will continue opening it up and then we have a look together. Okay, so I have removed all the screws around and now it should be possible to just lift this off from here. And here we are. And there's a protection here. Take this off and voila! This is how it looks from inside. So not much to see actually, unfortunately. On the up we have the BMS and then all these balance leads and connections to the cells, the power connections, and this here you see this is a pack. So one of those packs are a 2S pack. So there's 1, 2, 3, 4, 5, 6, 7 of these packs inside. And unfortunately we cannot look inside of this. So there inside will be many pouch cells, which you would find it in a tablet PC probably. So what I want to know now is if these cells are perfectly in balance or how this looks like. So let's check up the voltages. And 4.05. So first cell 4.05. This is about what we would expect from the 95% state of charge. Next one 4.05. 4.05. 4.05. The build quality is absolutely great. There's no flimsy stuff anywhere. And 4.05. 4.05. Okay, this means we had only 1, 2, 3, 4, 5, 6 points of measurement on this side. So where's the other ones? Probably on the other side, which we are not going to open. But as you could see, all cells have been perfectly balanced. Let me show you the BMS. There is really big power components there, MOSFETs. The resistors, they are also a little bit bigger, so they are responsible for balancing, resistive balancing. Also a very big aluminium plate here for heat dissipation. So quite a good quality build, I must say. Okay, I think we have seen enough. All the cells have been perfectly balanced, at least those we could reach with our probes. The other ones will be on the other side. Let's close this up again and then reinstall, and we are talking about how we are going to make the capacity check on this pack. So why in the first place did I buy this kind of battery? 3.5 years ago, lithium batteries have been very expensive. So for a big pack like this, even lithium iron phosphate cells have been very expensive. So the lithium-polymer cells, which have been used out of electronic devices more or less, this was the only one really affordable way of getting a lithium battery at that time. I have paid for that 10 kilowatt pack from the factory $2,000, so it's $200 per kilowatt hour, but of course this had to be shipped and it cost me around $3,500 from factory door to here to my door. How are we going to find out the remaining capacity of the pack? We'll do the test. There will be two parts. One is discharging first. Now we have a full pack there, and It will be out of the normal operation here. The discharge will be done by our garden lighting, same as every day. It is a constant load. We will then just look when this test started how much power we are pulling from the battery, and this we will then calculate over the time we will do the test until tomorrow morning. Maybe it will be around 13 hours or even 14 hours, and we will then just multiply the power by the time, and so we can see how much we have drawn. I don't want to draw the pack below my typical 25%, which I do every day, because I don't want to damage the cells. So I know my discharge curve and my state of charge pretty well due to the long time I'm using it. So we will then just see at which state of charge we have ended and how much power we have drawn of the pack. And then after we finish discharging, we will charge up the pack again and see how much DC power from the solar system is required to again fill it up. So we can then compare those two numbers and establish a pretty good number which should represent the actual state of charge. So the promised 80% after 500 cycles. How many cycles do we have? We have started to use this battery about 1100 days ago, and I am typically using 2/3 of the capacity every day, when the day is nice, of course, when I can use 100% of it. So my normal discharge goes to 25% on the low side and about 90% on the high side. So 65% or 2/3 of the capacity. That means from the 1100 days we only used 2/3 of them for a cycle. And then of course there's many days when the battery cannot be charged fully, you know, during the rainy season, during the monsoon time, when we have cloudy afternoons, etc. Some days will be just maybe 80%, 70%, some days not too many, will be also nothing, right? So for those we have to estimate also, and the estimation is that 20% of the remaining days we have is basically 0 days. So 65% multiplied again by 80%, and this comes to around 50%. So our estimation is that from the days we are running the battery, half of the days can be counted as full cycles, really 0 to 100%. So that means 1100, we are at the 550 cycle now, a full cycle. That means the battery should actually be below 80% remaining. So I think we will have still a better result than that, because lithium batteries, they like warm temperatures. In that room here where the battery system is inside, we have temperatures of around 30 to 34, 5 degrees all the year around. So it's a perfect temperature range for lithium-ion batteries. But let's see. Okay, so this is how we will do it. And now it's still afternoon. Before the sun is setting, we will then check up again and start the discharge test. Okay, it is now 6 o'clock in the evening, and we will start with the discharge test. We have a starting voltage of 57.4, which equals to 94% state of charge. The inverter is at the moment is idling. I have removed the grid power so that there is no input coming from the grid maybe. So we are purely on battery power. Solar does not matter during the night time, of course. I will now go and open our lights for the garden, and then we will check what power output the inverter has to deliver to run that. So usually our lights are switched by a light switch, but I can also override it manually. Let's do that. And the garden light is now on. Okay, what do we have here? So all the lights are pulling 360 watts. AC wattage 360, and we will cross check this by measuring the DC side as well. So I will connect the amp meter here on the battery, and we are pulling 7.1 amps at a voltage of this one is 1 volt too much, so 56.2. So on the DC side, of course, the amperage in the morning will be higher when the voltage is dropping, because the battery of course has to supply a constant load for the lighting. And yeah, we will then just check the time tomorrow and calculate how much energy was used. 6:20 in the morning. I just gave some rice to our wild chicken. These babes have been born here on our land. From here comes the old one. She flew in from somewhere. Okay, the lights are still on, and let's go and check inside. The test is still ongoing. 330 watts, and the voltage now 50.4. That is around 35% state of charge. So we can still continue a little bit. So I will say we will discharge until 8 o'clock. Time is over. It is 8 o'clock in the morning. We have a voltage of 49.8, and that equals to exactly 24%. So we went from 94 to 24, 70% of the pack was discharged. Our amp meter on the DC side says 8 amps. So that's about 400 watts again, same as we started. And this will be our reference value when we calculate the pack. Let's write it down. Okay, I will go and shut off the lights, and then we'll prepare the system for a charge. Before we can start with the charging test, we have to take all the loads now from the inverter away to the grid, so that we can just purely use the DC from the solar system to charge the battery. To do that, we have our transfer switch. I put it on manual and slowly turn it over. I'll leave it in this position a little bit so that all our equipment can settle down and does not have a voltage spike. Okay, so we are now, transfer switch is on grid, and I have a safety voltage relay. This one will now time out a little bit and then put the power again back on this loads center here. Okay, so it's back on. All loads are now on grid, and what we can do now, what we have to do is we have to prepare the measurement. I have my laptop here, and maybe you know it, here inside here is a meter. Because the inverter does not store any data, I have a meter here. You can see here is a shunt and then the black box, and this one I can read out via USB cable on the laptop, so we can then see how much energy was used from the solar system. So let me set this up quickly. We can now start with the charge test. So you see the voltage went up by 1/10 of a volt, because before we have been pulling a little bit of power and now it's idling. So we will take that as a reference for start. So the pack is at 25% now, and the meter is ready. We have to just note this energy value there as a starting point, because I could zero it out, but I don't want to, because this is my monthly generation meter here. Okay, 70, we are starting at 78.18 kilowatt hours, and let's now switch on the PV DC. We can check this here. Okay, now the solar has started to charge the battery. Here it says 450 watts. What does this one say? 467. So this one is much more accurate, of course, than the meter on the inverter. So this will give us a good readout later. Okay, it will take about 3 to 4 hours, so before lunch this battery should be full. It is now 11:30. We are pushing very hard, 3000 watts going into the pack at the moment, and that was after 5.5 kilowatt hours have been put inside. We are now approaching somewhere around 90% state of charge, and that will mean that the controller will then start to throttle down from constant current to constant voltage mode. And as soon as that happens, we will actually be satisfied and stop with the charging, because I don't need to go to 100%. 94, the starting point from the discharge test, is good enough. And here we are. So now the charge controller throttled down already substantially, and the voltage is already kept constant. I think if you now turn off the DC, it will be basically there where we started yesterday. So let's turn it off. And the voltage is 57.2. Yesterday we wrote down 56.2. This is because the that meter is showing 1 volt more, and we needed this to calculate the wattage. So it's the same as yesterday. We ended now at a state of charge of 94%. So you can see it here, 95, 57.7, and we are a little bit below. So 94, it's about there where we started. The test is now finished. I will switch the system back to the solar, and then we will sit down and calculate and check out the results. Okay, the results are in. Let's check on the numbers. So for the discharge, we always went from 94%. We went down to 24, 25, and then back to 94. The state of charge is based on voltage and the voltage curve, the charge and discharge curve of lithium-polymer. So I have a lot of experience with this pack, and I know the curve pretty well. We have taken out and then charged back 70% of the pack state of charge by voltage. The discharge, we only need to consider the DC side. It was constantly around 400 watts, so we take 400 watts for the calculation, and we discharged for exactly 14 hours. So 5.6 kilowatt hours have been used during the discharge. What is the difference between the 400 watt on DC side and on the AC? It was in average around 340. You see the difference. This is the inverter efficiency. The inverter efficiency, if you run it outside of its typical area, this is a 4000 watt inverter, and we only had a 350 watt load. So this is pretty far out of its perfect area, and so the efficiency is very low actually, right? So we had a inverter efficiency during the discharge of 85%. Okay, for the charge, we went then back from the 24 to 94 again, 70% state of charge according voltage. And for those 70% we have used 6.5 kilowatt hours of solar DC. MPPT charge controllers are very efficient usually, so probably somewhere around 97%, but we have also to consider other losses. So the typical charging efficiency for the DC side is somewhere around 93%. So we can assume that 6 kilowatt hours have gone from the PV into the battery. What does that mean now? Well, for the discharge, 5.6 kilowatt hours, which equals to 70% of state of charge, would then show us a remaining pack capacity of 8 kilowatt hours, or 80%. If we check that on the charging side, the 6 kilowatt hours, if that is considered to be 70%, then 8.6 kilowatt hours are remaining on that pack, or 86%. So the truth may be somewhere between those two numbers, between 80 and 86. This pack, after its 550 cycles, seems to be very close to what have been predicted that it will be. And yeah, I think it's still a very acceptable result. Degradation was to be expected. Everybody knows when he is using his tablet PC that after 1 year, 2 years, the capacity will drop dramatically. So it's still very, very nice result. Please, if you think that there was some serious flaw in the testing, what we have done, or you would have had a better idea of what you think the real result could be in this case, please leave a comment. I'm always open for inputs. So I hope you found it interesting, and please comment, like, subscribe, and I see you at the next video. Thank you.